Two creatures that live in permanent darkness, nearly 1,000 meters down, just washed ashore in Mexico. In Japan, they are called Doomsday fish, and the last time they appeared in numbers, a magnitude 9.1 earthquake killed over 20,000 people. Now, within the same 2 weeks, Louisiana just recorded the strongest earthquake in its history. Alaska triggered tsunami alerts, and Yellowstone's largest acidic geyser erupted for the first time in 5 years. Science says none of this is connected. Centuries of folklore violently disagrees. And the part nobody is talking about is that the scientists cannot actually prove they are right. And that is where this story gets interesting. Stay with me, because by the end of this video, you will understand exactly why nobody can tell you this means nothing. Subscribe and follow along, because this story is not finished. The fault system where those fish appeared is still being watched. The seismic window is still open. The researchers tracking these events are still running their models. And when the next development lands, this channel breaks it down first, and in plain language. You will want to be here for that. Now, let's get into it. Something washed up on a Mexican beach in late February 2026 that most people scrolled past without a second thought. Two enormous creatures, silver and ribboned, like something pulled from a nightmare, lay motionless on the sand in Cabo San Lucas. Beachgoers gathered around them, took videos, posted them online, and within hours, the internet had already decided what they meant. Doom. Because these weren't just any fish. These were oarfish. And if you know anything about oarfish, you know that their appearance on a shoreline is the kind of thing that tends to make certain people very, very nervous. The two animals measured somewhere between 10 and 15 feet each, although by the time the story had circulated through social media for about 6 hours, they had grown to 30 feet in every retelling. That's just how the internet works. But even at their real size, they are extraordinary animals. And the fact that they appeared at all was genuinely unusual. These creatures do not belong at the surface. They belong somewhere between 200 and 1,000 meters below the waterline, in a zone of perpetual cold and near total darkness, where sunlight has never once touched the seafloor. When one of them washes ashore, something has gone wrong. When two of them wash ashore at the same time, in the same place, people start asking questions. The location matters more than most of the headlines mentioned. Cabo San Lucas sits at the southern tip of the Baja California Peninsula, which is not just a beautiful stretch of coastline. It sits directly above the Gulf of California rift system, the southern continuation of the San Andreas Fault system, the same geological machinery that runs through California, the same network of grinding, slipping, building pressure tectonic boundaries, extends right down through this region and beneath the waters where these fish were found. That detail will matter later. For now, just hold on to it. Within the same 2-week window that those oarfish appeared, something else started happening. On March 4th, a magnitude 6.4 earthquake struck the Aleutian Islands in Alaska, triggering a tsunami evaluation and generating several aftershocks, including a magnitude 5.4. That same window brought a magnitude 4.9 earthquake to Red River Parish in Louisiana, which scientists confirmed was the strongest earthquake ever recorded on Louisiana soil. And on February 7th, just days before the fish appeared, Yellowstone's Echinus geyser erupted for the first time in over 5 years. One thing at a time, any of these events might get a brief news mention and then disappear. All of them together, in the same window, with oarfish showing up on a fault system, that's a different kind of story. Now, before we go any further, here's the disclaimer that every scientist will correctly give you. There is currently no proven connection between oarfish strandings and earthquakes. The scientific consensus is clear on this point, and we are going to take that seriously throughout everything that follows. But there is a reason this story has been told for centuries, and it is not purely hysteria. In Japan, these creatures are called Ryugu no Tsukai, which translates roughly as messenger from the sea god's palace. The name alone tells you something about how seriously Japanese coastal communities have historically regarded them. They are not merely a curiosity. They are a warning, or at least that is what the tradition insists. The most striking historical case is impossible to ignore. Before the 2011 Tohoku earthquake, which registered magnitude 9.1 and triggered the tsunami that killed over 20,000 people, approximately 20 oarfish had washed ashore along the Japanese coastline in the preceding months. 20 of them. That event remains one of the most catastrophic natural disasters in recorded history, and the fish had reportedly been appearing for weeks before the ground moved. That is either the most spectacular coincidence in the history of marine biology, or it is something else entirely. And the unsettling truth is that nobody can tell you with certainty which one it is. So here is the question that this story is really asking, underneath all the dramatic headlines and the viral videos of silverfish lying on the sand. Are we watching a set of random, unrelated events that our pattern-hungry human brains have stitched together into a narrative? Or are these events early signals from a planet under stress? Signals we do not yet have the instruments or the understanding to properly read? To even begin to answer that, we have to start with the creature itself. Because once you understand what an oarfish actually is, and what it is capable of sensing, the question becomes a great deal more interesting. There are animals in this world that exist at the edge of what biology seems willing to permit, and the oarfish is one of them. Regalicus glesson, to use its scientific name, is the longest bony fish on Earth. Not the heaviest, not the most powerful, the longest. Confirmed specimens have reached 36 feet, and there are unverified accounts suggesting they may occasionally grow longer than that. Imagine an animal the length of a school bus, shaped like a ribbon, covered in shimmering silver scales, wearing what looks like a crimson crown along its entire back. Now imagine it living in complete darkness, almost never seen alive by a human being, drifting vertically through cold water at depths where the pressure would kill you before the cold did. That is the oarfish. Its preferred zone is what oceanographers call the mesopelagic layer, sometimes called the twilight zone, sitting between 200 and 1,000 meters below the surface. Light from the sun reaches only the upper edges of this zone, and even there, it arrives as a dim blue wisper, rather than anything you would recognize as daylight. Below a few hundred meters, it disappears entirely. The oarfish lives in that transition, feeding on squid and small crustaceans, almost never interacting with anything at the surface, and almost never seen alive by humans. Most of what scientists know about them comes from dead or dying specimens that washed ashore, which is itself a problem we will come back to. When an oarfish does strand itself on a beach, there are several explanations that marine biologists reach for first. Illness and parasite infections are common, as they are with many stranding events across different species. Disorientation caused by unusual ocean currents can push animals far outside their normal territory. Temperature shifts, particularly the kind associated with El Niño events, can disrupt the thermal layers that these animals normally navigate by, essentially pulling the rug out from under their entire spatial orientation system. These are the explanations science is comfortable with, and for the vast majority of oarfish strandings, they are probably correct. But the oarfish has a few anatomical details that make the earthquake hypothesis harder to dismiss than it would be for most animals. Its eyes are enormous relative to its body, adapted for gathering whatever faint traces of light exist at depth. More relevant to our story, the oarfish possesses a highly developed lateral line system, a sensory organ that runs along the length of its body and detects vibrations and pressure changes in the surrounding water. This system is common to most fish, but in the oarfish, it appears to be especially sensitive, likely because navigating in near total darkness at pressure requires extremely fine detection of movement and disturbance in the water column. The lateral line is, in effect, a whole-body vibration sensor, and vibrations travel through water with remarkable efficiency. Sailors throughout history did not know any of this when they encountered oarfish. What they saw was a massive, serpentine creature at the surface, moving in slow undulations, silver in the sunlight, red crest rippling, and they drew the only conclusion available to them: sea serpent. The oarfish is almost certainly responsible for a significant portion of maritime sea monster accounts going back centuries. Submarine crews have occasionally reported seeing long, ribbon-like shapes in the water during dives. And while most of those accounts remain anecdotal, the oarfish fits the description better than anything else known to science. Here is where the story takes a turn that even some researchers are reluctant to fully dismiss. The hypothesis that has circulated in certain scientific circles, though it remains unproven, is that the oarfish's extraordinary sensitivity to vibration and pressure might allow it to detect something that our instruments are still learning to measure. When tectonic stress builds along a fault line, it does not simply stay silent until the moment of rupture. The rock does things. It shifts in microscopic ways. It releases gases. And according to one particular line of research, it does something else that almost nobody talks about in mainstream earthquake coverage. Something electromagnetic. And that is the piece of this story that changes everything. Rocks are not supposed to produce electricity. That is not something you learn in a basic geology class, and it is not how most people think about the ground beneath their feet. But under certain conditions, particularly when they are being compressed by enormous tectonic forces, rocks can do exactly that. The phenomenon is called the piezoelectric effect, and while it sounds exotic, it is actually well documented in laboratory settings. Squeeze certain crystalline minerals hard enough, and they release an electrical charge. Now, scale that up from a laboratory sample to a fault system bearing millions of tons of accumulated stress, and you start to get a sense of what might actually be happening in the rock before an earthquake occurs. The hypothesis works like this. As tectonic stress builds along a fault zone, the rock surrounding that fault begins to experience increasing compression. That compression can trigger the release of electrical charges, electromagnetic pulses, and ionized gases from the stressed material. These releases don't happen all at once. They can occur gradually, over days or weeks, as the stress accumulates toward whatever threshold will eventually produce an earthquake. And crucially, if they are occurring in rock beneath the ocean floor, those electromagnetic and chemical signals would propagate outward into the surrounding water column. The ocean, being full of dissolved salts and minerals, is actually a reasonably good conductor. Those signals would travel. This is where the fish re-enter the picture. Many fish species are capable of detecting extremely weak electric fields. Sharks, famously, use specialized organs called the ampullae of Lorenzini to detect the faint bioelectric fields generated by the muscle contractions of prey animals. But the sensitivity of some species goes beyond simple prey detection. Certain fish can navigate using the Earth's magnetic field. Others respond to pressure changes so subtle that they can effectively sense distant disturbances through the water. The oarfish, with its large lateral line system and its life spent in a zone where detecting any environmental signal at all is a survival necessity, may be among the most sensitive animals in the ocean to exactly the kinds of changes that a stressed fault system would produce. The Japanese researcher Kiyoshi Wadatsumi spent years investigating this idea formally, proposing that certain species of deep-sea fish might function as inadvertent biological sensors for pre-seismic activity. His work helped establish a field sometimes called ecological seismology, which takes seriously the idea that animal behavior might contain detectable patterns correlated with geological stress. This is not fringe pseudoscience being passed around on conspiracy forums. It is a legitimate research question that has been explored in peer-reviewed literature, even if the conclusions remain cautious and contested. The anecdotal record supporting animal earthquake precursor behavior stretches back thousands of years across dozens of cultures. Before the 1975 Haiqing earthquake in China, unusual snake activity was reported. Snakes emerging from hibernation in the middle of winter, which they do not do unless something has gone very wrong with their environment. Before several large Indonesian earthquakes, local fishermen reported fish behaving erratically near the surface before the ground moved. These accounts are not from credulous conspiracy theorists. They are from communities that lived close to the natural world and paid careful attention to it, because their survival depended on exactly that kind of attention. Here's where the scientists insert a critical and entirely fair caveat that we have to take seriously. Anecdotal reports are not data. They are observations made without controlled conditions, often recollected in the aftermath of disasters, and filtered through layers of cultural expectation and retrospective bias. It is human nature to remember the strange thing that happened before the catastrophe and to forget the 100 other times the strange thing happened and nothing followed. This is called retrospective bias, and it is one of the most powerful cognitive distortions in the human toolkit. The question is not whether animals behave strangely before earthquakes. The question is whether they behave strangely enough, consistently enough, specifically enough to constitute a reliable signal that could be acted upon. That question has a much harder answer, and that answer lives in the data. Statistics have a way of being deeply inconvenient to a good story. The most rigorous scientific study ever conducted on the relationship between deep-sea fish strandings and earthquake activity was published in the Bulletin of the Seismological Society of America in 2019 by researchers at Tokai University in Japan. They assembled what is genuinely an impressive dataset: 336 deep-sea fish appearances recorded over a multi-decade period, cross-referenced against 221 earthquakes of magnitude 6.0 or greater in the same region. This is not a small sample. This is the kind of analysis that should, if the folk wisdom has any validity at all, produce a detectable signal. The result was 1. Out of 336 fish appearances, only one case showed any correlation that could plausibly be called meaningful. 1. The researchers' conclusion was blunt. The connection between deep-sea fish strandings and subsequent earthquakes is most likely an illusory correlation, a pattern that appears to exist because our minds are constructed to find patterns, not because the underlying data supports one. That is the scientific position, and it is based on actual evidence, not skepticism for its own sake. The base rate problem is really the core of why the folklore persists, even in the face of evidence like this. Oarfish and other deep-sea fish strand themselves multiple times per year, across the globe, in all kinds of locations, and under all kinds of geological conditions. Earthquakes also occur constantly, with thousands of magnitude 3 and above happening globally every single year. When you have two phenomena that each occur regularly and somewhat randomly, you will inevitably get clusters where they appear together. Those clusters feel like meaningful coincidences because the individual events are dramatic and memorable. But the clusters are exactly what you would expect from random co-occurrence of two independent processes. This is called the base rate fallacy, and it is the reason humans see faces in clouds and conspiracy in coincidence. And yet, even the Tokai researchers noted something that gets lost in the summaries of their work. Certain clusters of deep-sea fish appearances did occur before some large seismic events, not consistently enough to constitute a prediction, not reliably enough to build a warning system around, but enough to prevent any honest scientist from saying the question is fully closed. The individual cases look convincing precisely because sometimes the correlation is real, or at least appears to be. In the 2011 Tohoku case, 20 fish before a magnitude 9.1 sits there like a splinter in the data that nobody has fully explained away. The paradox at the center of this question is that individual cases can look extremely compelling, while the aggregate data shows no reliable pattern. That is the scientific knife's edge this entire story balances on. What we are really talking about, when we push past the folklore and the statistics, is the difference between signal and noise. A signal is a piece of information that reliably indicates something real about the world. Noise is the random variation that surrounds every signal and can, if you look at it the wrong way, be mistaken for one. The oarfish might be a signal we haven't learned to read properly. Or it might be noise that only looks like a signal when something catastrophic follows, and we go searching backward for omens. Science cannot yet tell you which one it is, and that uncertainty is not a failure. It is an honest acknowledgement of how hard this problem actually is. Because while scientists were debating the fish, something else was happening across the North American continent that added a new layer to an already complicated picture. March 4th, 2026 started like most days in the Aleutian Islands, which is to say it started with geological tension that has been accumulating since before the first human being ever stood on those shores. At some point during that day, that tension found a release. A magnitude 6.4 earthquake struck the island chain, and for a brief window, tsunami evaluation protocols were triggered across monitoring stations in the Pacific. Aftershocks followed, including a magnitude 5.4, which in most parts of the world would itself qualify as a significant earthquake. Seismologists at monitoring stations watched the waveforms roll across their instruments, identified the location, assessed the depth and mechanism, and for the most part reached a familiar conclusion. This is the Aleutians. This is what it does. That context matters enormously and deserves more attention than it usually gets in media coverage. The Aleutian Islands sit above one of the most seismically active convergent boundaries on the planet. The Pacific Plate is being driven beneath the North American Plate along a subduction zone that extends for over 2,000 miles, from the Alaskan mainland out through the island chain and beyond. This subduction process is not smooth. It is punctuated by earthquakes, sometimes enormous ones. The 1964 Alaska earthquake, which remains the most powerful earthquake ever recorded in North American history at magnitude 9.2, originated from this same system. It generated tsunamis that crossed the entire Pacific and killed people as far away as California. The Aleutian Arc is not a curiosity. It is one of the most capable earthquake-generating systems on Earth. A magnitude 6.4 in this region is, from a pure seismological standpoint, not anomalous. These islands experience earthquakes of that size with some regularity. What seismologists watch for is not the individual event, but the sequence. Because the critical question when a significant earthquake occurs in a subduction zone is whether it represents a main shock followed by aftershocks, or whether it is itself a foreshock preceding something larger. The difference is not knowable in real time. The only way to know whether an earthquake was a foreshock is to wait and see if something bigger follows, which is an answer that helps no one who needs to make decisions in the immediate aftermath. That is one of the core, unresolved frustrations of seismology as a practical science. The timing of this event, sitting inside the same 2-week window as the oarfish stranding and the events that followed, is not something that seismologists would consider significant. The Aleutians produce magnitude 6 and above earthquakes regularly enough that finding one in any given 2-week period would not be surprising. But the story was just getting started. Because the strange part, the genuinely unexpected part of this 2-week window, was not what happened in Alaska. It was where the ground moved next. Louisiana is not supposed to have earthquakes. That sentence captures the general assumption held by most of the population of that state, and, frankly, by most people who do not specialize in North American seismology. Louisiana sits far from any plate boundary. It is not California, not Japan, not Turkey. It is low coastal plain, built from millennia of Mississippi River sediment, underlain by ancient geology that most people never think about. And yet, on March 5th, 2026, a magnitude 4.9 earthquake struck Red River Parish, roughly 5 kilometers below the surface, and the ground shook in a way it had never shaken before in recorded Louisiana history. That was the strongest earthquake ever measured on Louisiana soil. People in Arkansas and Texas felt it. That geographic reach matters because it tells you something about how unusual the event was. A magnitude 4.9 that crosses state lines in a region not known for seismic activity is the kind of thing that gets geologists paying attention very quickly. The question that immediately arose was the same one that has been circulating in the central and southern United States for the past 2 decades. Is this natural, or is this something we caused? Induced seismicity is the term for earthquakes triggered by human industrial activity, and it is far more prevalent than most people realize. The most documented case in the United States is Oklahoma. Before the widespread adoption of high-volume wastewater injection from oil and gas operations, Oklahoma experienced fewer than 2 significant earthquakes per year on average. By 2015, that number had exceeded 900. 900 earthquakes in a single year in a state that previously had almost none, and the culprit was not plate tectonics. It was the injection of enormous volumes of wastewater back into deep rock formations under pressure, which lubricates ancient faults and can trigger slip-along fractures that had been stable for millions of years. The USGS has documented this phenomenon extensively, and it fundamentally changed how scientists think about the relationship between industry and seismicity. Louisiana has a long history of oil and gas extraction. Red River Parish is not far from active extraction and injection operations, and USGS researchers were quick to identify induced seismicity as a likely contributing mechanism. That does not mean the earthquake was definitely human-caused. Individual events are rarely confirmed with certainty in these situations. The geological record beneath Louisiana contains ancient faults that predate any human activity by geological timescales, and those faults can slip on their own for reasons entirely unrelated to what happens above them. But the overlap between the location of this earthquake and the footprint of industrial injection activity in the region is the kind of thing that investigators do not ignore. And Louisiana was not the only unexpected place shaking. While the Aleutian Swarm and the Louisiana record breaker were generating headlines, a few other events were happening in places that received almost no attention at all. A magnitude 4.1 earthquake struck Nebraska on March 1st. The central part of that state is not somewhere most people associate with seismic risk, but it sits within a complex of buried ancient faults that occasionally remind the surface world of their existence. A swarm of small earthquakes rattled parts of South Carolina during the same general window, which would have drawn barely a footnote in any other context, but added one more data point to a picture that was becoming more interesting by the day. Midplate seismicity is one of the less glamorous but more genuinely puzzling areas of earthquake science. The standard mental model of earthquakes is simple. They happen at plate boundaries, where tectonic plates grind against each other, or one dives beneath the other. And that model is correct for the majority of the world's seismic energy release, but it is not the complete picture. Earthquakes can and do occur far from any plate boundary in the interiors of continents, along ancient fault systems that formed hundreds of millions of years ago under tectonic conditions that no longer exist. These faults can remain locked and dormant for extraordinarily long periods, then suddenly release stress that has been accumulating for centuries. The New Madrid seismic zone is the most consequential example of this in North American history. Stretching across parts of Missouri, Arkansas, Tennessee, Kentucky, and Illinois, this zone is underlain by an ancient rift system that the continent tried and failed to tear itself apart along roughly 500 million years ago. What remained is a network of deeply buried faults, and in the winter of 1811 and 1812, those faults did something that nobody alive at the time had any framework for understanding. A sequence of earthquakes estimated at between magnitude 7 and magnitude 8 struck the region in a series of catastrophic events over several months. Church bells rang as far away as Boston. The Mississippi River, briefly and surreally, appeared to flow backward as the land deformed on either side of it. Sand blows erupted across the landscape as liquefaction events turned saturated soil into something closer to liquid. Today, that same zone sits beneath one of the most densely populated river corridors in North America, largely unprotected by the kind of building codes and emergency infrastructure that California has developed over generations of hard experience. Scientists know that ancient faults remain buried beneath the continent, and they know that stress can reactivate them. What they do not know is when or exactly what triggers that reactivation. That question sits at the edge of what seismology can currently answer. And meanwhile, back on the coastline where this story began, the oarfish had appeared along something that turns out to be far more geologically significant than most of the coverage suggested. Cabo San Lucas is known to most of the world as a resort destination. Clear water, dramatic rock formations, sport fishing, cruise ships. What it is less known for, at least in popular conversation, is that it sits at the southern terminus of one of the most geologically active tectonic systems on the western side of North America. The Gulf of California rift system is not a minor geographical footnote. It is a zone of active seafloor spreading, where the Pacific Plate is pulling away from the North American Plate and new oceanic crust is being generated from below. Baja California is not technically part of the North American Plate in the way that most of Mexico is. It is being carried northwestward on the Pacific Plate, which is why the Gulf of California exists at all. The peninsula is slowly pulling away from the mainland at rates that are geological in human terms, but represent enormous accumulated energy over time. This rift system is the direct southern continuation of the San Andreas Fault System. The same fundamental tectonic motion that produces earthquakes in Los Angeles and the Bay Area, the same grinding boundary between two massive plates, runs southward through the Salton Sea, across the border, and becomes the network of transform faults and spreading centers beneath the Gulf of California. Historically, this region has generated numerous earthquakes in the magnitude 6 to 7 range, and larger events are entirely within the geological capacity of the system. When you draw a straight line from the San Andreas Fault southward to where those oarfish washed ashore, you are drawing a line along one of the most tectonically active corridors on the western edge of the continent. To be completely clear about what the science says, there is no evidence that those fish strandings were caused by seismic activity in the Gulf of California system. Marine biologists have better and more mundane explanations for why oarfish sometimes reach the surface, and those explanations do not require earthquakes, but the geography is what it is. Two animals that live in the water column above a major active plate boundary appeared at the surface of that water, on the shoreline closest to that boundary, within a 2-week window that also contained the strongest earthquake in Louisiana history, a seismic swarm in Alaska, and the reactivation of a geyser at Yellowstone that had been silent for 5 years. You can call that a coincidence. The evidence suggests you are probably right to call it that. But there is something about the spatial and temporal clustering of these events that the rational mind wants to sit with for a moment before moving on. And then Yellowstone's alarm system went off. Echinus Geyser reactivated on February 7th, 2026. For most people, that sentence contains at least one word they have never heard before. Echinus, pronounced Akynus, is not one of the geysers that appears in most Yellowstone tourist photography. It is not Old Faithful, erupting on schedule for coach buses of visitors. It is something considerably stranger. Echinus is the largest acidic geyser on Earth. Its pool measures roughly 66 feet across. Its pH sits between 3.3 and 3.6, which puts it in the same acidity range as vinegar, approximately the chemistry of a stomach. It erupts every 2 to 5 hours when active, sending water 20 to 30 feet into the air, and it has been doing this at various intervals for longer than any human record keeping can trace. It is located in the Norris Geyser Basin, which is one of the most thermally active areas in Yellowstone, and, by extension, one of the most thermally active areas anywhere on the surface of the Earth accessible to ordinary people. Norris sits above a junction of fault systems that allows unusually direct access between the surface and the hydrothermal system below. Temperatures in some Norris features can exceed the boiling point even at depth, which is rare even by Yellowstone standards. The basin has a documented history of periodic disturbance events, periods when the entire hydrothermal character of the basin shifts. Features go quiet, others come to life. The ground temperature changes. Scientists call these disturbance events, which is one of geology's more understated nomenclature choices for what is essentially the largest natural plumbing system in the world, having an unpredictable episode. Aquinas had gone dormant in December 2020. For just over 5 years, its pool sat quiet, filling and draining without erupting, a cold version of something that used to be spectacular. And then, in the first week of February 2026, it came back. The eruptions returned, the interval between them settled back into the 2 to 5 hour rhythm, and rangers at Yellowstone began receiving more visitor interest than the basin typically generates in February. The timing, sitting 3 weeks before the oarfish and inside the same general window as the seismic events, is the kind of detail that the internet does not let pass quietly. But to understand why scientists are not panicking about Aquinas, you need to understand something about how Yellowstone actually works beneath the surface. Yellowstone sits above one of the most geologically bizarre structures on the surface of this planet. Beneath the national park, a massive magma reservoir has been mapped by seismologists using the same techniques that doctors use to image the inside of a body. The shallow part of this reservoir, sitting somewhere between 5 and 17 kilometers below the surface, contains a mixture of partially molten rock and crystal that may represent somewhere between 5 and 15% actual melt by volume. Below that, extending down to depths of around 46 kilometers, a second, larger reservoir has been identified, and below that still, a column of hot material rising from somewhere in the mantle. Yellowstone is not just a geyser field. It is the surface expression of a geological system that extends hundreds of kilometers into the Earth's interior. The hydrothermal system is powered by the heat this magma releases upward. Groundwater circulates through fractures in the rock above the reservoir, picks up that heat, and eventually finds pathways back to the surface. Where those pathways are constricted and the pressure can build, you get a geyser. Where water reaches the surface more freely, you get a hot spring. Where the chemistry changes due to the specific rock types the water passes through, you get something like Aquinas, where acidic gases dissolving into the water create a pool more hostile to life than almost anything else in the national park. The system contains somewhere between 500 and 700 active geysers, roughly half of all the geysers on Earth, making Yellowstone a geological anomaly of the highest order. Geysers switching between active and dormant phases is completely normal behavior within this system. The underground plumbing that feeds any individual geyser can be modified by earthquakes, by changes in the water table, by shifts in the pressure regime within the hydrothermal system, by mineral deposition that slowly clogs or opens channels over time. Old Faithful itself has shown measurable changes in its eruption interval following major distant earthquakes. The 2002 Denali earthquake in Alaska caused temporary changes in geyser activity at Yellowstone more than 3,000 miles away, which tells you something about how sensitive these systems are to seismic vibration. Aquinas going dormant for 5 years and then reactivating is, from the perspective of hydrothermal system dynamics, well within the range of expected behavior. The USGS Yellowstone Volcano Observatory maintains one of the most sophisticated monitoring networks on any volcanic system in the world, tracking seismic activity, ground deformation via GPS networks sensitive to millimeter scale changes, gas emission chemistry, and water chemistry in thermal features. As of the time this story was developing, their monitoring data showed no unusual uplift of the caldera, no significant changes in gas emission chemistry, no seismic swarms indicating magma movement. What it showed was a hydrothermal system doing what hydrothermal systems do, behaving unpredictably within its normal range of variation. The USGS conclusion was calm and technically well supported, but Yellowstone's reputation is not something that calm technical language easily overcomes. Yellowstone's last super eruption occurred approximately 640,000 years ago. The scale of that event is genuinely difficult to hold in the mind. The eruption deposited volcanic ash across most of the western half of North America. It would have darkened skies on a hemispheric scale, altered global temperatures, and reshaped the ecological character of an entire continent. This is not speculation or exaggeration. The geological record is clear on what happened. Ash from that eruption has been found in sites as far away as the Gulf of Mexico. The caldera it created is roughly 34 by 45 miles across, large enough that most visitors to the park drive around inside it without realizing that is what they are doing. This history is why any unusual activity at Yellowstone generates immediate and intense public attention. And that attention is not entirely irrational. A system capable of producing an eruption of that magnitude deserves to be watched carefully, and the USGS does watch it carefully, with resources and sophistication that did not exist a generation ago. But the media and public response to events like the Aquinas reactivation frequently moves straight from hydrothermal change noted to supervolcano about to erupt, skipping over the vast and scientifically important territory in between those two statements. Hydrothermal activity is not volcanic activity. Those are related but distinct systems, and changes in one do not automatically indicate changes in the other. Scientists sometimes use the metaphor of a pressure relief valve. The geyser field acts as a way for the system to constantly bleed off energy and pressure, which is actually the opposite of an eruption scenario. A completely sealed, featureless caldera with no hydrothermal activity would be more alarming in some respects than one with active, changing geysers, because at least the active system is demonstrably releasing pressure through familiar channels. The presence of a giant magma reservoir beneath a place that has geysers waking up after 5 years of dormancy sounds terrifying. Statistically and scientifically, it is far less alarming than it sounds. But here's the thing about human psychology and rare catastrophic events. We are not naturally calibrated to handle them. We are calibrated for predators on a savanna, for weather patterns that affect the next harvest, for social threats within a group of 100 people. We are not calibrated for 640,000-year geological cycles, or for the base rate of supervolcanic eruptions on a geological timescale. And that miscalibration leads somewhere very specific and very interesting. The human brain did not evolve to be a good statistician. It evolved to survive, and survival across most of human history meant noticing patterns fast, acting on incomplete information, and being wrong occasionally in a way that cost you nothing, rather than being slow and right in a way that got you eaten. That cognitive toolkit is spectacularly well suited for a world of immediate physical threats, and it is genuinely terrible for evaluating the probability of rare geological events. The psychological phenomenon driving most of the public response to stories like this one is called apophenia, which is the human tendency to perceive meaningful patterns in random or unrelated data. Apophenia is not a disorder or a failure. It is the baseline operating mode of a pattern recognition system that kept your ancestors alive. The same cognitive mechanism that makes you see a face in wood grain, and a conspiracy and coincidence also allowed early humans to notice that a particular animal track preceded a predator, or that a specific cloud formation preceded a storm. The pattern finding was adaptive. The problem is that it does not come with an off switch, and it fires just as readily on random noise as it does on genuine signals. Stock traders see patterns in market movements that are statistically indistinguishable from random walks. Astrology persists in the face of a complete absence of supporting evidence, because the pattern-matching system finds its correspondence between planetary positions and personality types intuitively satisfying. And when oarfish appear on a fault line the same week that unusual earthquakes hit 3 different states and a dormant geyser wakes up, the pattern-finding machinery in the human brain goes into overdrive. There is a version of this story where everything we have discussed is random noise that happened to cluster in time, and our brains dressed it up in meaning after the fact. That version is probably correct. The statistical evidence, as we have seen, does not support a causal connection between most of these events. But there is another version, less comfortable and more interesting, where some of these events are connected by mechanisms that science does not yet fully understand, and our instruments are too crude and our sample sizes too small to detect the signal buried in the noise. That version cannot be ruled out either. Earthquake prediction remains one of the most genuinely difficult unsolved problems in all of science. Our current systems detect earthquakes after they begin. They cannot tell you one is coming, and that is not for lack of effort. It is because the Earth is complicated in ways that continue to exceed our ability to model it. The events at the center of this story may be coincidence dressed up as warning, or they may be warning dressed up as coincidence. And the fact that we cannot, with the tools and knowledge we currently possess, definitively distinguish between those two possibilities is not a reason for panic, but it is a reason to keep asking the question. Allow yourself for a moment to take the folklore seriously. Not because folklore is always correct, but because sometimes the patterns that non-scientific cultures developed through thousands of years of close observation contain real information that formal science has not yet caught up to. If the oarfish hypothesis is correct, if these animals do possess some biological sensitivity to pre-seismic electromagnetic or pressure signals, then what we would expect to see is strandings occurring days or weeks before significant earthquakes in tectonically active regions. Not always. Not reliably enough to build a warning system on, but more often than pure chance would predict, particularly in areas of genuine geological stress accumulation. There is actually a broader possibility here that researchers in ecological seismology find genuinely interesting. If fish can detect electromagnetic changes from stressed rock, what about other animals? Chemical changes in groundwater can precede earthquakes, and animals that interact closely with groundwater might be the first to notice. Changes in radon gas emissions from stressed fault zones have been documented before some seismic events, and burrowing animals or species that breathe air from soil-poor spaces would be directly exposed to those changes. Toads in the lake at L'Aquila, Italy, evacuated their breeding site 5 days before the 2009 earthquake that killed nearly 300 people. The behavior was documented in real time by a researcher studying breeding populations, not recalled after the disaster. That is one of the few cases in this entire literature where the animal behavior observation predates, rather than postdates, the earthquake it supposedly predicted. None of this constitutes proof. None of it rises to the level where you could build a reliable warning system. But it suggests that the biological monitoring of animal behavior might eventually contribute to earthquake early warning systems in ways that current technology cannot replicate, because animals are doing something that our instruments are not. They are sensing the world continuously, at multiple spatial scales, through multiple physical channels simultaneously, in real time, at essentially zero infrastructure cost. The challenge is not finding the signal. The challenge is distinguishing it from the endless noise of ordinary animal behavior in a world where animals are constantly doing strange things for perfectly mundane reasons. Let us be equally rigorous about the mundane explanation, because it deserves the same careful treatment as the folklore. The 2 oarfish in Cabo San Lucas almost certainly washed ashore because one or both were ill, injured, or disoriented by ocean current anomalies, possibly related to the ongoing evolution of Pacific Ocean thermal patterns. Oarfish strand themselves every year, globally, and the vast majority of those events are not followed by earthquakes, because the vast majority of events of any kind are not followed by earthquakes in the immediate short term. The appearance of two of them simultaneously in the same location is unusual enough to be noteworthy from a marine biology perspective, but it is not unprecedented, and it does not require a seismic explanation. The Alaska magnitude 6.4 happened because the Pacific Plate is subducting beneath the North American Plate in the Aleutians, as it has been doing for millions of years, and the accumulated stress periodically finds release through earthquakes, as it has been doing for millions of years. The Louisiana magnitude 4.9 happened in a region where oil and gas extraction has been altering the stress state of ancient faults for decades, in a zone where USGS researchers have documented induced seismicity with increasing frequency. The Nebraska magnitude 4.1 and the South Carolina swarm are consistent with mid-plate seismicity from ancient fault systems that have nothing whatsoever to do with what is happening in Alaska or Louisiana or Mexico. An Aquinas geyser reactivated because geysers and dynamic hydrothermal systems do that, independently, for reasons having to do entirely with the local underground plumbing, and the USGS has found no indicators of volcanic unrest at Yellowstone. These are independent events with independent causes, sharing only the 2-week window in which they happened to occur. The human mind experienced them as a connected narrative because the human mind is extraordinarily good at constructing narratives. But narrative is not causation. The timing creates a compelling story. The evidence, taken individually and examined without the emotional weight of the clustering, points toward coincidence. That is the honest scientific assessment. And yet, it does not fully close the question, because coincidences of this apparent density do occur. And when they occur near active fault systems, the question of whether something is being missed stays open longer than it would anywhere else. This is not the first time this pattern has appeared in the historical record, and the repetition itself is worth examining. Before the 2009 L'Aquila earthquake in Italy, the toad migration event was documented. Before the 1975 Haicheng earthquake in China, the snake behavior was documented and actually used, controversially, to inform a successful evacuation order that saved tens of thousands of lives. That event remains one of the only cases in history where an earthquake was officially predicted with enough confidence to justify an evacuation, and the animal observations were part of the evidence base that informed that decision. The earthquake struck hours after the evacuation, at magnitude 7.3, and the city center was largely empty. 2 years later, the 1976 Tangshan earthquake struck a different Chinese city without warning, killed somewhere between 240,000 and 700,000 people depending on the source, and produced no successful prediction despite occurring in the same country, with the same monitoring apparatus in place. That failure haunts the field of earthquake prediction to this day, because it demonstrated that the success at Haicheng might have been partly luck, partly good geology in a system that was behaving unusually distinctly, and not necessarily a transferable methodology. The animals behaved strangely before Haicheng. Whether they behaved strangely before Tangshan is not well documented, which tells you something about the quality of the evidence base. Fish erratic behavior before Indonesian earthquakes, unusual animal activity before the 2004 Indian Ocean earthquake and tsunami, birds abandoning coastal areas before the 2011 Tohoku event. The pattern keeps appearing across cultures, across centuries, across species. Either this is the most persistent and widespread example of retrospective bias and mass illusory correlation in the history of natural observation, or there is something real embedded in this record that we have not yet found the scientific framework to properly investigate. Both of those possibilities are genuinely on the table. And the fact that they both remain on the table, after this much time and this much scientific effort, tells you something important about the current limits of what we know. Here is what makes this story genuinely remarkable, and it has nothing to do with folklore or coincidence, or even earthquakes specifically. Humanity has built instruments capable of detecting gravitational waves generated by the merger of two black holes more than 1 billion light-years away. We have mapped the cosmic microwave background radiation left over from the first 380,000 years of the universe's existence. We can detect individual neutrinos passing through the Earth, particles so small and so weakly interacting that billions of them pass through your body every second without touching a single atom. Our sensitivity to the universe at cosmological scales is extraordinary beyond easy comprehension, and we cannot reliably predict when the ground beneath Los Angeles will move. We cannot tell the people of Tokyo whether the next magnitude 9 is 3 years away or 300. We cannot give the residents of the New Madrid seismic zone the kind of warning that would allow meaningful preparation for an event that the geological record tells us is inevitable on some time scale. After everything we have built, after all the satellites and seismometers and supercomputer models, earthquake prediction remains one of science's genuinely humbling, unsolved problems. Not for lack of effort, not for lack of intelligence, but because the Earth is a non-linear dynamic system of staggering complexity operating across scales from the subatomic to the continental, and the signals that precede rupture are buried in noise in ways that our current mathematical tools have not cracked. The events we covered in this story are almost certainly coincidental. The oarfish, the Alaska swarm, the Louisiana record, the Nebraska rumble, the geyser. If a major Pacific earthquake strikes in the weeks following this video, these events will be remembered as harbingers, their significance amplified retroactively by everything that followed. If nothing dramatic happens, they will fade quietly from memory, recalled only by people who were curious enough to follow the story and then moved on when the narrative failed to deliver the ending the pattern seemed to promise. That is how it almost always goes. The omens that are not followed by disasters disappear. The omens that are followed by disasters get written into the historical record and passed down through generations. But the real mystery here is not the fish. The fish are a proxy for a question so much larger that it almost does not fit inside a single story. The mystery is what the Earth might be doing before it breaks, what signals it might be sending through the rock and the water and the electromagnetic field, through the behavior of creatures that have been living in proximity to geological systems for hundreds of millions of years, through channels of communication that we have not yet learned to listen to. The fish might be messengers. The data suggests they probably are not, at least not in any reliable and actionable way. But the fact that we are still not sure, after everything we know, is the most telling detail of all. Because if the Earth is speaking, and we still cannot hear it, that says less about the Earth than it does about the instruments we have chosen to listen with. And somewhere in the darkness below the surface of the Pacific, a 36-foot ribbon of silver scales drifts through water that has not seen sunlight in 1,000 years, sensing things we cannot measure, waiting for something we cannot predict, indifferent to what we choose to believe about what its appearance might mean.